Thank you for coming the day before spring break. All right, yes, exactly. And the weather turned okay right away, right in time. So the last time we have talked about the human thermochemistry, and we have talked about nutritional thermochemistry. And you have seen that the nutritional calorie is 1 kilocalorie. It's 1,000 calories. So that's the big C, all right? And that means if you have to eat 2,500 calories per day, this is 2.5 million calories as you know them. And we don't use calories anymore. We use joule as energy. 1 calorie is 4.18 joules, right? And we calculate it in joule. So 2,500 calories per day is 2.5 million calories per day, or times 4, about 10 million joules per day. This was what you need if you want to function properly. If you eat more, you will gain weight, or you have to work more, you have to exercise more. I think Michael Phelps, he needs 10,000 calories a day. Yeah? But I don't think that anybody of you will need 10,000 calories, except if you are in rowing, in crew, there you will burn a lot of calories. And so how much is that? We talked about power. Power is given in watts. That is 1 joule per second. If 1 joule per second is used up, that's 1 watt. Okay? You have a light bulb that has 100 watts that uses 100 joules per second. That's what you pay for on your meter, electricity meter. Most of the energy, of course, will be not given off as light. It will be given off as heat with a regular standard light bulb. If you have an incandescent light bulb, if you have a fluorescent light bulb, that's about a factor of 8 or something less. So most of it is given off as light. That's why you only need a 13-watt light bulb to get the equivalent of a 100-watt incandescent bulb. Okay, so we get the same light. So that's how we save energy. So if you just operate on your regular level, that you breathe and you keep all your functions going, you need about 100 watts per second. So all day you need 100 watts, and this will bring you, remember we had 10 to the 7th joules per day. If I want to get to 100 watts per whole day, the day has 10 to the 5th seconds about. So this will give you 100 watts a day. So this will sustain you. This is like walking extremely slowly is 100 watts, whatever you need. You're using up 100 watts, okay? So we then talked about the thermochemistry of the metabolism. You eat food and you breathe in oxygen, you get CO2 out, and water. So essentially, you have a state function. You put food in. This is usually carbohydrates, most of our food, carbohydrates, and you have then, in a lower energy state, you get CO2 and water. The formation of CO2 and the formation of water gives that release of energy, okay? And, of course, to be honest, some people are not metabolizing their food as well as others. Some people, they can eat, as we say, like a horse, and they are thin like a rail, okay? And so much of the energy is not burned up. They get it out in some other way again without using all the energy that was in the food. And some other people, and this is true, they just look at a piece of food, they gain weight, okay? And we know those also. I belong probably to those. Not necessarily, I don't only look at it. So this is the metabolism also plays a role in this. But thermodynamically, we can say we eat something, we use oxygen, and then we make CO2 and water. Of course, the efficiency is only 70%, something like this. All right? But you will know this when you go into this kind of field to study it. So sugar has 4 food calories per gram. So this is 4,000 chemical calories per gram, and a gram, an American pound, has 454 grams. So if you multiply this times 454, you get about 1,800 large calories per pound of sugar. If you do this with fat, fat has more than double the calories, a gram of fat, so you get about 4,000 calories per pound, and this is why the storage of energy is much more efficient in fat than in sugar. You would need to have twice the size, twice the mass than you would have to have with fat. So all the people who are a little bit heavier, they would be even more heavier, even much heavier than they would have when they have their fat belly, okay? And so we also talked about Snicker bites, and a Snicker bite, these tiny little things, they have about 50 calories, so that's 50,000 calories. And so then we talked about this possible diet that you get to 2,500 food calories by eating 50 Snicker bites a day, so then you can sustain yourself with 100 watts all day long. I don't recommend it, okay? And then there is also the first time from home undergraduate student diet, where you can eat donuts all day long, and they are 400 calories a donut, so you will need about 6 per day to get enough energy to function. But you don't live very healthily, and you won't function very long, okay? So you need to have a balanced diet, so these 2,500 calories can come from all kinds of balanced dietary sources. That's the important part. So today we're going to talk more about thermochemistry, and we're talking about bond energies. So remember, when we have hydrogen and oxygen, and we react them with each other, we blow the hydrogen and oxygen up together, what do we make? What do we make? Water, okay. And so there is bonds formed between hydrogen and oxygen. It makes one hydrogen and another hydrogen bond to the oxygen, which is water. So the bonds are formed. Is there energy released? Yes. When bonds are formed, energy is released. And this bond energy is the energy that that bond has, okay? It takes you exactly the same amount of energy to take it apart again, all right? And then to take it apart, you have to put that energy in to pull the bonds apart. That's the bond. It holds that together, and in order to separate it, you put that energy in that it released when it was formed. And now you have it separated. So when you have to separate, you break bonds. Is this exothermic or endothermic? Breaking bonds. Endothermic, okay. That comes maybe from, anybody had AP in biochemistry? Okay, the teacher was very good probably, but it's a high likelihood that he or she said, you know, the ATP bond, when it breaks, you get energy. And this can be used then in the next reaction. That's what they say? That's totally wrong, okay? When you break bonds, if you break an ATP bond to make ADP, what do you do? Do you gain energy? No. You need to put in energy to break it apart, all right? So the question, of course, is where does the energy come from? It's the hydrolysis of ATP that will release energy. That's an exothermic reaction, okay? Remember, when you break bonds, you always need energy, right? So you break somebody's neck, you need energy, all right? Good. Maybe you remember it then. That's all I'm hoping for. So let's get right into it. So we have determined the energy of a reaction by looking at let's do this first. So when we have here a compound XY, it has bonded, it's in a low stable energy state. Now we want to take it apart into X and Y. We're going to break that bond. All right? So we need to put in energy to get X and Y atom now. So the individuals are now, the two atoms, are each of them at a higher energy state than the compound before. So now I could take this again, and now I let it form bonds again. So this is endothermic. If it forms bonds again, I would release energy. So there it goes. It releases the same amount of energy that it took to separate it. With this, I went up, I broke the bonds, then I reformed them, I'm at the same energy state than I was before. Okay? So this is something we can use. Oh no, let's first talk about breaking of bonds. So you have carbon, solid carbon. I talked about graphite. It's a sp2 hybridization. You don't need this to answer this here. But solid graphite. So we want to atomize this. Atomize means we want to make individual carbon atoms in the gas phase. All right? So there is a possibility to do that. So I'm asking you now, how many moles of carbon-carbon bonds are broken when you atomize 1 mole of carbon? Is it 1 mole, 2 mole, or 4 moles? Why don't you think about this? And I would do it this way. I would take 1 carbon atom, and I wouldn't take necessarily the one on the outside, 1 mole, so the effects on the outside are not that important. It's the bulk effect. So I would take 1 atom and draw some bond, and then I take the next one, and the next one, and the next one, and the next one. Why don't you give us a stab here? Let's see what you come up with. If you come up with the obvious or with the right answer. So that's an average, okay? Don't go on the outside and try to make it, but just in the inside. How many? How many? Guess is good, huh? Didn't guess? Excellent. Okay. Oh, I'm talking with your colleagues here, and you're waiting. So there is a 4. It's not 1, they say, because I have these letters right there. That's probably true. But now it's between 4 and 2. Why don't you discuss this with each other and try to give me one unified and hopefully the right answer, okay? Please discuss this. I know it's hard, but you could also talk about what you're going to do during spring break, okay? But have a discussion. I wouldn't know the difference. Yeah, I would go with B. Why? You create a carbon lattice. You take 1 carbon, and you do 2 bonds. You take the next carbon, 2 bonds, 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 the next carbon, 2 bonds. There it is. Well, so where is it coming now? There, the next carbon, 2 bonds. Where does this go? Probably here. The next, and there, that's how you do your lattice, okay? So that means that the creation of the carbon lattice requires 2 cc bonds per carbon atom. What does that mean? You get, for 1 mole of carbon solid that you atomize, you get 2 moles of carbon bonds broken, okay? So, oh yeah, that's right. I did, but that would be not good if I give you a different explanation. So let's talk a little bit more about bond energies and how we can derive reaction enthalpies from bond energies. And I will explain to you in a little while why we want to do that. So we have reactants and they are in a certain energy state, initial energy state, and let's say we're going to have an exothermic reaction. Exothermic reaction, so we go there to our products. The products are lower in energy, so we have given off energy. That means the delta H naught of the reaction is negative. Okay? I also could have done this. I could have put this up here. Then delta H naught of the reaction would have been positive. But let's discuss just this case where we have the release of energy. So the other possibility, I do this. I take the reactants and I break all the bonds of all the reactants. And I get them all as single atoms. So I do this. I have now the atoms. So the energy that I need is the energy, the sum of the energy of breaking all the different bonds, okay? And this is positive. Because I break bond, I need to put in energy, all right? Now we have the atoms. Now we're going to do, and it finds its partner to make the reaction product. So we say, okay, we make these bonds. For the new reaction products, we make these bonds. And so we need to have the sum of the bond energies for the atoms making the products. And this would be a value, would be still a positive value, but we have to subtract it because we are making now bonds, okay? So the difference is this plus this, and since this is negative here, we will get a negative number, and we are actually now, we have a circular process. So if I calculate this, if I know these bond energies and these bond energies, I calculate this, I should get the delta H naught of the reaction, the heat or the enthalpy change for that reaction, okay? So that would be one possibility. That's what I just told you. You take the bonds of the energy to break these bonds, the sum of those, minus the energy to make these bonds. The minus sign is because you release energy. You just take the absolute number here. And with this, you get this delta H naught. The other possibility is we make enthalpies of formation. What does that 0 mean? At standard state, okay? Enthalpy of formation at standard state. And what is the standard state of these tabulated enthalpies? It's 1 molar for solutions or 1 atmosphere for gases. And at 25 Celsius, which is 298.15 Kelvin, all right? So I said enthalpy of formation, I always omit the standard state. I said delta HF naught. That would be, for example, how I would say it sloppily. So if I make the elements, take the elements and make the compounds, that would give me the delta HF of the formation, formation, yeah, the enthalpy of formation at standard state. So why don't I go the other route? I take the elements, and we know carbon, for example, is not 0. Carbon is a solid, and the enthalpy of formation is for the carbon gas, okay? So that was the carbon, no, the carbon solid was, so I need some, no, the carbon solid was 0, okay? But in order to make carbon gas, so I now break the bonds. To make carbon gas, okay, I need energy. I have the carbon atoms, and then I have oxygen here, and O2 was 0, but I knew we need to break the bonds of the oxygen, so I would need some energy. So I make carbon and oxygen, so I need energy. This is the amount of energy I need, okay? Now I form the bonds. What do I want to form? I want to form CO2. I take one carbon and two oxygens, and so I form these bonds. I calculate what this is. This is the sum here, and I take the minus here. With this, I should get the same number by going this route here. So this is actually an imaginary route. It's very difficult to put them in the gas phase, then have them react in the gas phase, and then put them back as solid CO2, or a CO2 whatever gas, or whatever we want here. So this is something, it's called a circular process. That's called the Hess process. We can have any way, you could make all kinds of processes as long as you get from your element to your compound, okay? And this is the nice thing about the state function, that it only depends on the beginning, on the end. So we went up here, we went down here, beginning and end, we should get the same energy change. All right, so far we have looked at the standard enthalpy of formation, and we know now why the standard enthalpy formation of hydrogen and oxygen and nitrogen gas is positive. Why is that positive? Because the standard state is oxygen 2, nitrogen 2, and hydrogen, 2 molecules, 2 atoms, okay? You have to break them apart. Do you need energy? Yes. So this is the energy you need to break that hydrogen bond, the oxygen bond, and the nitrogen bond, okay? And we have talked about all these energies here. So now we're going to look at the bonds, and these are all positive numbers, because if we break the bonds, we need that number. If we make the bonds, it becomes negative, okay? So to break a hydrogen bond, you need 463 kilojoules per mole. To break a chlorine bond, 242 kilojoules per mole. So you see, you need 497 kilojoules per mole to break an oxygen double bond, but only 146 to break an oxygen single bond, all right? So the other possibility would be that we have HCl. To break an HCl bond, you need 431 kilojoules per mole. Nitrogen, huge strengths, bond strengths. You see that? 946 kilojoules per mole to break this nitrogen. It's a triple bond here, okay? Now, these are all absolute values, because there's oxygen, which you can break, nitrogen, which you can break, HCl that you can break. But the moment you have carbon involved, when you have carbon involved, then they become average numbers. They're average numbers. Many of you had maybe a little bit of organic chemistry or biochemistry. So the carbon bond, or bound to anything else, depends very much on its chemical environment, okay? If there are some other groups that pull, for example, on the electron density, then that bond is weaker. So if you have carbon bonds, these are averages. They are not absolute numbers. So we can use this to estimate energy changes in large molecules, for example. And I will talk about this in a moment. But first, I want to give you an example. And the example is the following. We have our bond energies there. Let's make some, what shall we make? Let's make some HCl. If I could have the camera on me on the screen here, and some lights, please. Let's make some HCl. If I ever... Okay. So we want to make HCl. So I need your help with this. And we want to make the delta H naught of HCl formation, okay? Is, what is it, joules or kilojoules per mole. Can you read this up there? Can you read it? Okay. So what do we need to do to make HCl? We need to take hydrogen, and we break a mole of hydrogen bonds. Yeah? So this would be 436. That's the hydrogen. We break the HH, okay? 436 hydrogen bonds breaking. And then we need to take chlorine. Isn't it chlorine? Plus, what is chlorine? How much energy we need for breaking chlorine? Call it out for me. I can see very well. 242. 242 kilojoules per mole, this would be this here, okay? So, and now we say, we're making bonds, now we're making HCl, isn't that right? What would that be? 431 kilojoules per mole. All right, this is HCl. But there is something wrong. What is wrong? How many moles, if you break hydrogen or chlorine bonds, how many mole of hydrogen or chlorine do you make? You break one bond, you break 1 mole of bonds, but you make 2 moles of hydrogen for each mole of bonds that you break. So you have 2 moles of hydrogen, 2 moles of chlorine, so you must make 2 moles of HCl, okay? Let's write this times 2 here, okay? So what does this give us? That gives us so what is that here? That's 431 times 2 is 800 minus 862, okay? And this is 678, is that right? 678 minus 862 is now minus 184 kilojoule per how many moles? Per 2 moles. 2 moles, okay? So how much would it be per mole? 92. It's 92 kilojoules per mole. I divide this by 2, all right? And if you look this up in the literature, or in your table, you find 92.4, just from the measurement. So this works very, very well to estimate these enthalpies of a reaction. So I could have also taken this here and divide this by 2 first, and divide this by 2, and then have 431 only. That would be the same. Okay, let me come back to why we use the organic chemists are using this, and especially the molecular and biology people, and cell biology people, because very often, thank you, you can shut the light down now. Very often you have these large molecules, huge protein, and there are literally tens of thousands probably different molecules, and you cannot measure the enthalpy of formation of all those. It's impossible. But most of the time, there's only one little reactive center where there's a couple of carbon bonds, carbon-carbon or carbon-oxygen or carbon-nitrogen or carbon-hydrogen bonds are broken and reformed. So the biologists or the cell biologists or the biochemists, they say, okay, this bond is broken and this bond is broken, this CH, that and that and that, and this is reformed and this reformed. The difference is this, the rest is the same, so I can calculate if it's negative, it's exothermic, if it's positive, it's endothermic. So it gives you a very nice way for estimating enthalpies of reaction for essentially unknown organic molecules, because there's only a couple of things changing, and you know what the estimates for the bond energies are, and with this you are home free. You can get an energetic balance there without having to measure 10 millions of different compounds to get the enthalpy of formation of those. Okay? You got this? Important for you. All right, let me ask you another question. You remember when we stood here and people were holding hands, and then they did like this, they were ethylene, and then they became polyethylene. So now think about this again. And we polymerize ethylene to polyethylene. So why don't you use these 3 and count, okay? So we polymerize ethylene to polyethylene. So this is breaking of a CC double bond, and making of CC single bonds here, okay? You have to, of course, be right how many you make. Is this an exothermic or an endothermic or a reaction where there is no change in energy and enthalpy at all? Why don't you think about this and give me your answer? So maybe I can give you the table a little bigger here, okay? There's the table. So you have CC doubles And you have CC singles, obviously. So how many CC doubles do you have and how many CC singles do you make? Okay, many of you say endothermic, some say exothermic, and some say it's a wash, it's not no energy change whatsoever. I think you need to come to a conclusion here, and you are making, obviously you're breaking double bonds and make single bonds. So how many double bonds are you breaking and how many single bonds are you making? There lies the answer. Why don't you discuss this with each other, please? Come on, let's have a discussion. What is it? No. I'm sorry that I had to send it in color to this time. What? I had to send it in color this time, the handout.
Oh, I ran out of ink.
You're done? Okay. I hope we're done. All right. Wrong direction. I go for exothermic. So that's why we do these chem quizzes. I said, why didn't I think about this? Okay. So you have one double bond. An average. How many single bonds you make? 2. Okay, so you make twice the amount of single bonds. To break one double bond, you need 612 kilojoules per mole. But then you make 2 single bonds. This is 696 kilojoules per mole, and this is negative. 612 minus 696, okay, is a negative number, all right? And with this, it must be exothermic. Let's see what the answer says here for you, that we have it again. So you have, why didn't you use these 3, for example? So you have 3 double bonds, makes you 6 single bonds, okay? We were standing there, okay? The number, if you have n double bonds, you have 2n single bonds. The number is n is the number, okay? So with this, I just calculated it for you, And with this is, if you have twice this always and single this one, so this is the larger number, that's negative. So if you have the smaller number and you have a negative larger number, that means you will have a negative number. And with this here, there it is, it's smaller than 0, and it's exothermic. Let's do another one just for fun, okay? Oh. Okay. We can even use this theory if you are sharp, which I know that you are, but maybe not this afternoon. But if you are sharp and you have learned this kind of reasoning, which is difficult to do, okay, you can use this to determine structures. So I give you the following example. So we can leave this on here. We have hydrogen peroxide, H2O2, and it decomposes to water and half a mole of oxygen. 1 mole of water, 1 mole of hydrogen peroxide, 1 mole of water, half a mole of oxygen, and this releases heat. It's exothermic. So that means the delta H got to be negative, okay? So what is the molecular structure of H2O2? Is it B, double bond, an H here and H here, double bond, an H here and H here, or is it an H on each oxygen and a single bond between them? Why don't you think about it and give me an answer? It's very simple, actually, once you know how to do it. Everything is simple once you know how to do it. You will say, why didn't I think of that? Okay, there's oxygen single bonds, and there are oxygen double bonds. Don't get confused by the OH bonds. That's a hard one, but solvable. I bet you some of you can solve that. After I told you, everybody can solve it. You got to give me everything you got here. All right. Interesting. Interesting. Okay, let's talk a little bit more about this. So we have OH bonds. We have 2 OH bonds and 2 OH bonds here. Isn't that right? So you break OH bonds, you make the same bond, forget about them. Okay? So now you have a mole of oxygen here, and you make some OH here. There we said we forget about those. Okay? You have a mole of oxygen here, you have a half a mole. Okay? And this is where the answer lies, actually. So why don't you think? And I told you it's exothermic. Why don't you discuss this with each other? Don't be too stunned. Good idea would be buying new batteries for your eye clickers, just as spring break and bring new batteries the next time. Just take the old ones out and put new ones in. I see everybody's changing batteries. Obviously, they're going soft on you. It's exothermic. That's the key. Okay, let's see. Yeah, I go with A. Why? So we have, this is our reaction. So we have 1 mole of H2O, we make half a mole of oxygen and 1 mole of H2O. So I have 2 OHs here, and I have 2 OHs here. That's a wash. We don't have to break and make them. That's a wash, okay? So now, if I have here, if this would be a double bond, I have 1 mole of double bonds. Is that right? Okay. If this would be this here or that here, I have 1 mole. But now oxygen, is this a double bond? Oxygen? Molecule, single or double bond? It's a double. So you may have 1 mole of oxygen you have to break of double bonds, and you make 1/2 mole of oxygen double bonds. Would that be exothermic or endothermic? So you have 1 mole of oxygen, 612, minus 1/2 mole of oxygen. You make 1/2 mole minus 306. So this would be still endothermic, would be plus 306, okay? But I told you it's exothermic. So it only can be exothermic if you have, this is what I just said, this would be endothermic. Now if you have a single bond, okay, you have 1 mole of single bonds is 348 kilojoule, all right? And then you make 1/2 mole of, oh, yeah. The numbers didn't jive, you know. I said, what? So you have, so I was pointing there before at this one? Okay, so I do it again, okay? If you have, I actually calculated it, yeah. Fortunately, it came out right, yeah. So you have a mole of double bonds is 497, okay? It's even more drastic, okay? And then you make 1/2 mole of, this is the half of it, that's 250, 240, 46 or something, or 47 and a half or something. Yeah? And so that would be a positive number. Good. Thank you. and so if it's exothermic, I break a mole of single bonds is 146, and I make 1/2 mole of oxygen is minus 497.5, which is about 250, minus 250. So the difference is a negative number, okay, minus 100 about, yeah? And with this, we know this could have been only that, all right? Easy once you know how to do it. Let me ask you another question. A quick question, and everybody needs to have this right, otherwise I'm devastated, okay? So you have a 1 mole of, you know, we do combustion. I'm not going to let you go into spring break without having some fire or something going on here, okay? Or some combustion. So we have a 0.1 mole of butane, and that's a gas. And we have 0.2 mole of butane. And here we have 0.1 mole of butane and 0.1 mole of oxygen. So we put them all here, one after the other. I shall separate them from each other, shouldn't I? We put them in front there. So I need your help now, and it will not be loud at all. It will only be warm, okay? We're releasing heat. So I want you to help me be my sensors, not with the lips, but with your hands, okay? How about these 2 rows here? So you hold out. You can't resist, okay? You hold out your hands like this, and then you tell me afterwards which released the most heat, okay? So this is the one, what was it, 0.1 mole of butane. Careful, careful. Now the next one. Are you ready? What was that? Hotter. You answered that question already? No. Oh, I should not have done that. Okay. I am looking so forward to this, you know. So now let's watch this one. So, why don't you answer that question? Let's see. I ask you then, okay? Why don't you answer this question and tell me what you think? And you don't be quiet. You just answer it your way, okay? Then we ask our monitors, our living thermometers, or heat sensors. Which one released the most heat? You're not yet, later. You tell me, first you click in. Okay, click in. Everybody in? Oh, you should have this down pat by now, okay? So let's see what our heat sensors, our human heat sensors say. Which one was the hardest? A, B, or C? C, you said C? And who says B? Let me tell you a story. If you go and fill your car up, usually you have maybe $5 in the pocket. You fill your car up, but you didn't have 5, you only had 3. So you fill your car up with 1 gallon, and the next day you have $6 and you fill it up with 2 gallons of gas. What do you think will go longer? Okay, why don't you answer that again? I'll show you. Yes. 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 That was just faster. Can I have the glasses back, please? You don't want these old, beat-up glasses. Got it, yeah. Thank you. Thank you. Okay. Everybody in? Yeah, obviously you're having your discussion. Everybody in, come on. All in. So much data now in there. Excellent. See, the gas help. Of course, you remember, it's dependent on the mass, okay? You have twice the mass of butane, and this would be, there's just a little faster. This was faster. This all had to find the oxygen in the room, but this was faster. But this was essentially the same energy than this one, and this has double the energy released, okay? With this, the answer was that. I wish you a happy spring break and see you Monday in a week.